Welcome back to another lesson in MCV4U. Today we'll be talking about piecewise functions. Piecewise or split functions is a function whose equations is split into two or more parts. Its graph can look like a combination of several disconnected functions on the same grid. When we graph a piecewise function, it's sometimes helpful to create a table of values, and we'll do that in the examples that we see below. However, to start, what I would like to look at is to look at the graph of y is equal to the absolute value, so the absolute value of x. And these two vertical bars indicate, again, so let's write that. So y is equal to the absolute value of x. And what these vertical bars will indicate is that for any x value, the corresponding y values will be positive. For any x values, the corresponding y values will be positive. Okay, so here, let's take a look at our table of values. So again, we'll draw a table of values right here, and we'll have our x values and our y values, which are the absolute value of x. So we'll go from -3 to +3. And here, again, any x value, the corresponding y values will always be positive. So here for -3, we will have +3. For -2, we'll have +2. For -1, we'll have +1, 0, and then 1, 2, and 3. So if you notice here, -3, -2, and -1 change to 3, 2, and 1. So here, as we look at it, we see that the bars flip the sign. And that's for -3, -2, and -1. For 1, 2, and 3, the bars had no effect. That's important as we continue to look at this absolute value function. So let's sub in these values into our graph. So go 1, 2, and 3, 1, 2, and 3, 1, 2, 3, and -1, -2, -3. So we'll just label our graph here. And as we can see, if we sub in our values, so we'll start at -3, will be +3. At -2, it'll be +2. At -1, it'll be +1. 0 will be 0. 1 will be +1. 2 will be +2. And 3 will be +3. So if we see this graph here, it looks like a V-shaped. And again, what we notice is all the y values are greater or less than 0. As we can see, they don't cross the x-axis, and they all are positive values in this situation. So let's think about it here. So here we have f of x is equal to the absolute value of x. Okay. But again, if we get rid of the absolute value, or the two vertical bars, then all we're left with, if we want to split it up, is, again, we have just x by itself. Here, if we write our notation, we just have x by itself. And so we have to indicate two branches. So this would be our first branch. This would be our second branch. So we're going to create some parameters and when we look at this absolute value graph. So we know again that f of x, the y values have to be greater than 0. So we know that the y values have to be greater than 0. So if we have x, if we're looking at the negative and we're looking at the positive. So x, when x is less than 0, and here we have x when x is greater than 0, or greater than or equal to 0. However, we have a bit of an issue. If we sub in just x is equal to 5, or x is equal to -5, what does that give us if we don't have those absolute values? Right? If f of x is just equal to x, therefore x will be equal, or f of x will be equal to -5. Again, if we sub in another value, let's say x is equal to -10, f of x is equal to x, that provides us, again, with -10. Now, the issue that we're running into is with the negative values and the negative branch of this absolute value function. So how can we make it so that this value of x becomes positive? And so if we think about it here, if we put a negative sign in front of this x, then suddenly these x values will become positive. So here, instead of it being -5, we have negative times -5, which will be equal to 5, and that's what we want. And if we put negative, -10, that'll give us +10, which is also what we want. So now we can see that the parameters that we have are correct. And we can see here in this function, there is a change in direction at a specific spot. And that change in direction is at x is equal to 0. So it's important when we put these parameters, you see that when x is less than 0 is going to be -x, but when x is greater or equal to 0, then it just is x, right? So as we see, if, for example, if we just put x is equal to 2, we don't want the -x, because if we sub in f of x is equal to x, sorry, f of x is sorry, f of 2 is equal to x, then we see here that it is equal to 2, which is what we want. So again, with the positive value. Okay, so as we see here, we indicate that this value of 0 is a few things, and you can describe it in a few ways. You can describe it as a root, or you can describe it as an x-intercept. So the 0 value, again, is written as the root or the x-intercept. So what we just did there is these absolute value functions can be written in two pieces. One piece where the bars acted and one where they didn't. So we see how in this situation, this is the one that the quote unquote bars didn't act. And this one is where the bars acted. Okay, so if we keep looking at this, so here if we write again, it's where again the roots or the x-intercepts. So if we look at the function of x, again the absolute value of x minus a. So this is again where the root or the x-intercept is. Here, the y value has to be greater or less than 0. And here we can write our two branches. So here we have our first branch and our second branch, just like we saw here. So remember, you have one branch, again, that is from one side of the root or the x-intercept, and we have another branch that represents the other side of the root or the x-intercept. And so that's why we represented it as x minus a. So here we have two conditions we can write. So again, x minus a is less than 0, and this would be for the negative side. Or if we move that over, we know that here it would represent as x is less than a. And for the positive side, we have x minus a. So this is for the positive side, is greater than 0. Here, x is greater than a, or x is greater than that root. And as we saw here, as we write it in these two branches, one would be negative x minus a, and the other one would just be kept as x minus a. In our situation, or our first example, we wrote it as negative x, and it would have been minus 0, but again, we don't have to write that. And the other one would have been x minus 0, just by itself there. So let's take a look at these examples here. So it says, write the function f of x is equal to x minus 2 in piecewise function here. So let's look at that. So again, write the function of f of x is equal to absolute value of x minus 2 in piecewise form. So there's a few things that we can look at here. So the first thing is that we can note that, again, remember there's one branch where the actually absolute values or the bars actually act on these values. There's another branch where they do not act. And so we have to take a look at that there. Okay, so it says write the function f of x is equal to absolute value of x minus 2 in piecewise form. So if we put this, again, the bars will act when x minus 2 is less than 0. So again, the bars will act when x minus 2 is less than 0, or we can also again write it as x is less than 2. So again, if it's left of 2, then the bars will act. Therefore, we see that it's going to be negative x minus 2, as you saw there. If it's right of 2, then the bars do not act. And here, that would be just x minus 2, as it was in the absolute value function. So here, if we write it in this notation, so again, it's called piecewise form, we will get f of x equal, we, we use this large bracket to indicate our piecewise form, negative x minus 2 as x is less than 2. and x minus 2 when x is greater or equal to 2. So again, it follows the same understanding that we had in the first question and in these parameters that we put on when we looked at these conditions. Okay, so let's look at this third example here. And this third example says, sketch the graph of f of x is equal to x minus 2, or absolute value x minus 2 over x minus 2 on the grid. Then use the graph to examine the limit when x approaches 2 from the left, x approaches 2 from the right, and as x approaches 2. So put those with the function in mind. So again, we can see that just like we did before, x minus 2 is less than 0, and we know that x would be less than 2 if we move that over. When we look at the function, then we can rewrite that in a couple of ways. So let's look at the larger function here. If we write that in piecewise function, you see that from the negative side, or when x is less than 2, see here that if we go negative x minus 2 over x minus 2, we see here that the x minus 2 is going to cancel out. And because they cancel out here, that means there is going to be a hole at x is equal to 2. So it's going to be a hole at x is equal to 2. So when we look at the positive, we have x minus 2 over x minus 2, and those would also cancel out. And that again is when x is greater than 2, greater or equal than 2. But here we have to think about, does it equal to 2? It doesn't in this situation because there is the restriction. So not equal to 2 because of the domain restriction. So here we see that it's just going to be x is greater than 2. So usually we would write it as x is greater or equal to 2, but because there is a hole and a restriction on that domain, we no longer write x is greater or equal to 2, we simply just write x is greater than 2. So now we can rewrite this here as f of x is equal to -1 when x is less than 2, and +1 when x is greater than 2. So let's draw this on this graph. So we have 1 and 2, and here we have -1 and +1. So just label these. So we see here that when x is less than 2, it is at -1. So when x is less than 2, it's at -1. And we know that here there is a hole at x is equal to 2. And we represent that by an open circle. Here we see that when x is greater than 2, there is also a hole, and it's at 1. So the graph is going to look like that. Now we have to evaluate the limits. So the limit as x approaches 2 from the left of this particular function, we can see here that it's approaching the left, and we see that that's going to be at -1. So again, approaches 2 from the left, we see that that's going to be at -1. Here, the limit as x approaches 2 from the right of this particular function, that's going to equal to 1. And remember, one of our criteria for these limits was that, again, the left-hand limit and the right-hand limit have to be equal for this limit to exist. And in this situation, they do not, and therefore we can see that the limit as x approaches 2 of this function does not exist. So let's look at this last example here. This should be example number 4. It says sketch the graph of f of x is equal to absolute value x plus 1 over x squared minus x minus 2 on the grid. Then use the graph to examine the limit as x approaches -1 from the left, the limit as x approaches -1 from the right, and the limit of x as it approaches -1. So the first thing we want to do here is, again, let's write the function. Here we can factor out the bottom. So again, thinking about our factoring methods, we can factor this out, and the two values that the x squared minus x minus 2 will factor out to are x minus 2 and x plus 1. So let's write that down. So here we have f of x is equal here to again, we'll look from when x plus 1 is less than 0 first. So here, x plus 1 is less than 0, or x is less than -1. So looking from that parameter, we now understand that's going to be negative x plus 1 over, as we saw the factors, x minus 2, x plus 1. So we see here that x plus 1 can cancel out. And so we know that x is equal to -1. It's going to be a whole. So x is equal to -1 is going to be a whole. Okay, and then for when x plus 1 is greater than 0, or x is greater than -1, here we see the same thing. Again, we have x plus 1 over x minus 2, x plus 1, and we see that the x plus 1 will cancel out here. And so if we rewrite the function here, so we rewrite this function, we can see that f of x is equal to -1 over x minus 2, and that's when x is less than -1. And we can see that 1 over x minus 2 when x is greater than -1. We also notice here that we have a vertical asymptote. And that vertical asymptote is when x is equal to 2. So again, we have a vertical asymptote when x is equal to 2, and we have a hole when x is equal to -1. Okay, so let's graph these two functions here. So we'll start with when x is less than -1. So we'll do two table of values here. So do 1 when x is less than -1, and we'll do another one where x is greater than -1. But we'll start with when x is less than -1. When x is less than -1, the function will be f of x is equal to -1 over x minus 2. And so if we sub in values of x being less than -1, so we can start again here with -1. We start with -1. We see that that is going to be at 1 over 3, and that's where our hole is. So this is where the hole is, just so we remember to do it when we put in the graph. At -2, it'll be at 1 over 4. -3, it'll be at 1 over 5. And -4, it'll be at 1 over 6. Okay, so let's graph this first. And so we'll have these values here. So we'll have these values of -1, -2, -3, and -4. And then we'll also have our y values of 1 over 3, 1 over 4, 1 over 5, and 1 over 6. So let's indicate that here in our graph. So -1, -2, -3, -4. And this will be 1 over 6, 1 over 5, 1 over 4, and 1 over 3. And this will go from -1 to -4. And so here we see at -1, there'll be a hole at 1 over 3. And then at -2, it'll be at 1 over 4. -3 will be at 1 over 5. And then it keeps going here, and it continues down. So that's the first part of our graph. If we look at our second part of this graph, that's again when x is greater than -1. So we'll put another graph here, or another table of values, and then put it on the graph. So this will be when x is greater than -1, and f of x will be equal to 1 over x minus 2. And so here we'll start with -1, 0, 1, 2, 3, 4, and 5. And so at -1, we get a value of -1 over 3. And remember, this is where the hole is. At 0, we get -1 over 2. At 1, we get -1. At 2, if we sub it, we see that we get 1 over 0, again, which means that here it does not exist. And that makes sense because that's where our vertical asymptote is. At 3, we get 1. At 4, we get 1 over 2. And at 5, we get 1 over 3. So again, remember, x is equal to 2 gives us our vertical asymptote. Let's write that down as well. So now let's graph the rest of this. So if we graph the rest of this, so here we have, again, -1 over 6, -1 over 5, -1 over 4, and -1 over 3. Here we'll go 1, 2, 3, and 4. And so we can finish graphing this. So here again, we see at -1, we have another hole at -1 over 3. And then we see that 0, it's going to be at -1 over 2. And so we can graph that here. So both here, and then it continues down. Okay, and then we see that at x is equal to 2, there's going to be a vertical asymptote. So let me just draw that. So this is x is equal to 2. That's going to be our vertical asymptote. And then we can draw the graph on the other side. When we get to 3, it goes to 1, and then 1 over 2 and 1 over 3. And so the rest of the graph will look something like this. It goes up and continues here as well. Okay, so here again, we looked at the absolute value function, and then again, how to split it into a piecewise equation or piecewise function as well.